We good, Roy? Yep. Okay, so first, I hope this meeting is helpful. I'm kind of going to present these topics assuming that people have very little experience with either of these things. I'm also not an expert, so I know there's some people in here who would know a lot more than I do potentially. So feel free to chime in when I say something wrong or if there's something that you want to elaborate on. Anyway, so we're going to talk today about profiling and debugging on like Linux, Macs, anything that's not Windows basically. So I just want to make a confession right off the bat, which is that debugging in Windows is way easier than debugging, especially C++. If you debug C++ in Windows with Visual Studio, it's a very, very nice system. Would you agree, Jim? Yeah,
I would agree.
Jim agrees. So you're not going to get exactly the same level of functionality, but we can get you like almost all the way there. We can get you really close, and so if you're using Linux, you're kind of just stuck with that point. So there's nothing you can do about that. So, okay, so let's get starting. So the topic today is on debugging and profiling, and I was going to start with profiling because I think it's cooler, and it may be something that a lot of you haven't seen before. But for those of you who don't know, profiling is basically the process of seeing where your program actually spends its time running. So the output from the profiling program called gprof is a big text file that has a list of basically every function in your program and how much time your code spends there, how much time you spend in the function, how many times you call each function. It's super useful. So if you write a big code and you get to the point where it kind of works but you want to speed it up, you can either kind of blindly poke around and guess where it's spending all its time, or you can use gprof, and gprof will tell you exactly where it's spending all its time. And today we're going to do a real-world example with my code, which is an awesome code. So, so you'll kind of see what that's like. So I thought that I would just start with just a really simple example, because I think that's always the best way to start. And sorry if this looks not organized, because we had to deal with this room change. So I wrote this little program called test.cpp. It's a little C++ program, and it doesn't do much. All it does, going to the end here, here's main. All it does is it has a function called setA, which creates a really big matrix that's 10,000 by 10,000 elements. It sets it to random numbers. Then the second function transposes it, and this third function computes the trace of the matrix. So it's a super simple program, and its point is just to demonstrate a really basic debugging output. So you can see there's three functions. There's setA, transpose, and trace. So I'm just going to go ahead and tell you how you would use gprof to get some useful data from this program. So I'm going to suspend this. So first thing you have to know is that you have to compile your program using the -pg option. And that, I'm pretty sure, is also true of the Intel compiler. It's the same option for Intel. And I did a test, and Intel output you can still use gprof to examine. So that's good. So I'm going to give the -pg option, and I'm going to compile my code. Yes. And then all you do is you run your code, like you normally would. So I'm going to run it. And it takes a couple seconds, because it's kind of a big matrix. And then it's done. So you'll notice that this file called gmon.out was generated by the program when I ran it. Gmon.out is this file that contains all this information now. So to run gprof, you just do gprof, and you might think you do gprof gmon.out, but you don't. You do gprof and then the name of your executable. So I don't know why that is. Does anyone know why that is? I don't know why that is. Okay, that's just the way it is. And then if you do that, it's going to spit out a whole bunch of information. So I'm going to pipe it into less like this so we can look at it. So here, the output from the profiler is divided into two areas. This is the first area, is this little table up here. Again, because our program is so simple, there's not a lot of functions in it. But you can see here that you get this little table. And what this table tells you is basically which functions take the most time. And it orders them, it puts them in that order. So what this table tells us is the transpose function, you can see under the name column, takes 56.49% of the runtime of my program. It was called once, and I think this is seconds per call. Right? So this is useful because you may have a function that takes 50% of your runtime, does very little, but is called like 10 million times, so it just takes a long time to run. And then this number here is the key number, which is actually how much time it's spent in that function. So what you can see from this little table is that this program spends the most time in transpose. As you might have kind of guessed, it spends 56% of the time there. It spends 43% of the time in this function called setA. Then you're going to see a bunch of random stuff because of C++. But you can see it spends 0% of the time in this random stuff, so that means you don't care about it. And then way at the bottom, because trace is such a simple operation, it takes almost no time in the trace function. Good? Okay. So that's the first chunk of the gprof output. And then the second chunk is this table here. So one thing I want to iterate is that this table here, when it says it spends 56% of the runtime, that is just in the function itself and not anything that function calls. Right? Because, so if transpose doesn't actually take a long time, but it calls some other function that does take a long time, transpose won't be at the top of this list. Does that make sense? So if you want that information, what you go is to the second part. Okay, so what you might expect is that the main function, which contains everything, takes 100% of the runtime, which it does. So this second part of the table is organized so you can see how much time a function takes and how much time everything that function calls takes. And it has kind of detailed data about like how much time it spent in each of its children. So this tells you that main took 100% of the runtime, because you're in main until you quit. It spent basically 0 seconds in itself, and it spent 2.62 seconds in its children. So children means functions that it calls. And then what it does is it lists the functions that main calls. So main calls 3 functions: transpose, setA, and trace. So it says that. So you go to the next line and it says, when main called transpose, it spent 1.48 seconds in transpose, and then it spent 1.14 seconds in setA, and is basically 0 seconds in trace. And then this number here just says that 1 of 1 means that transpose was called a total of 1 times, and it was called 1 time by main. So when we go to Cooper, my code's example, these numbers are going to be more meaningful. Okay, so this is the data for main because there's this little number. Oh, I shouldn't point. There's this little number 1 here in brackets. So whatever the number in brackets is next to, that's like the section for that function. Okay, let's look at something else. So if we go down to transpose, this is transpose's section because it has this little number 2. Transpose doesn't call anything, so there's no functions below transpose. But transpose is called by main. So the functions above the line with the little number in brackets are the functions that call a given function. So in this case, for transpose, the lines above it indicate what functions called transpose. And since transpose calls nothing, there's nothing below transpose here. Okay? And it's the same thing for setA, because setA doesn't call anything, but it gets called by main. And you can see there's very similar data. One thing I want to point out is what this second column here is. So this column says that main called transpose. Transpose spent 1.48 seconds in itself and 0 seconds in any of its children because transpose didn't call anything else. Okay, so you can see how using this output you could create like this tree where you see exactly where your program spends its time, and you would think that someone would have created this tree because gprof's output has not changed in like 20 years, and it's like not a hard program to make, but like such a program I don't think exists.
There's a lot of programs that read gprof.
Oh, really?
Yeah, they give you visual output.
Do you know their names by any chance?
I don't know them offhand, but I can probably find them.
Yeah, if you could email me, I'll put them on the website. Because that's something I've been looking for, and I just did a quick Google, and I couldn't find anything. So I'm I'm happy to be wrong in that.